Hello everyone and welcome to the second course on the subject of diodes and DR two-port networks. Last time we discussed about the general structure of the DR two-port networks and some applications, namely the positive half-wave rectifier and the negative half-wave rectifier. Today we continue our discussions on the DR two-port networks by introducing a load resistance. If you remember from the last course, our DR two-port network looked something like this. So we had the input VI, go. Let me draw this a little bit better for you to see. So we had the input VI, which is connected to our DR circuit, composed of a diode and a resistor. And we saw a few configurations of this DR circuit, and this circuit is connected to the output where we measure the output voltage. And today we discuss about the behavior of the DR two-port network when there's a third resistance involved, known as the load resistor. Generally, we don't work with a load resistor when it comes to DR circuits, because this load resistor is most of the times considered to be a drawback, and we'll see why this is. So let's draw a DR two-port network. We have a voltage source, we have a diode, and a resistor. So of course we have the usual parameters: the voltage across the source, or the source voltage, the diode, and the resistor. However, we are now introducing a second resistor, the load resistor. In this circuit, as you can see, our load resistor is connected in parallel to the regular resistor, and the voltage is measured like so. So from this point to this point, we're basically measuring the voltage, the output voltage across the R resistor. This means that RL has no influence on the circuit whatsoever, as this output resistance on which we measure the output voltage, the R resistor, basically only changes its value to the equivalent resistance of R and RL. So R is in parallel with RL. And we can say that the equivalent resistor, the equivalent resistance, will be equal to R times RL over R plus RL. And this is our new value for the output resistor. In theory, whether we use this circuit with R and RL, or we use this circuit, which I'm going to draw right now. So like I said, in theory, it should not matter if we use this circuit with two resistors in parallel, or the equivalent resistor or the equivalent resistance of the two previously mentioned resistors, R and RL. So this is our equivalent. It should be the same thing, and it is, as we're going to see through simulations. Okay, so make sure to pay attention. This R and RL resistors, these two R and RL resistors are in parallel, and it doesn't matter if we work with this circuit or the other circuit, the output should be the same. And to see that happens, I'm going to open OrCad this time. I'm going to open the project in which I already created the circuits. And these are the first two circuits, so this one and this one. I'm just gonna move this a little bit more to the right so they don't interfere. So these two circuits, this one and this one. In the first circuit we have R4, which is our R resistor, equal to 1 kilo, and R5 is 3 kilo. R5 in our case is the load resistance. The parallel equivalent resistor between 1 and 3 kilo would be 0.75 kilo ohms, which is the value of R6, and R6 is the equivalent resistance. If we do an analysis, namely a time domain analysis, we'll see that if we measure the output and the input, of course, for both circuits, they will be absolutely the same. So this is the first circuit. We're going to add another plot pane, and in this second circuit we're going to use, well, we'll try to use like this. There we go, it worked. So the first circuit, our input voltage is this one, the one marked with red. I'm going to change its color to green, and then the output, I'll switch it to red, so they have the same colors. And if you're asking, yes, these two waveforms are exactly the same. Going to make the output voltage a little bit bolder so we can see it better. So just from looking at these two waveforms, you can tell they're exactly the same. Okay? And if you want further proof, let's look at the maximum voltage of the output for both waveforms. So to do that, we'll evaluate measurement. We need the maximum voltage across the first diode, VD1. In the parts and currents, we don't need that. So VD1 2, which is 9.26, and the same measurement for the second diode. So ED22. Which is again 9.26. So it's the same exact value, as you can see. Going further, this means, like I said, that the load resistor doesn't really have an impact on our circuit, only that it basically changes the value of the resistor, well, of the output resistance. But we don't need two resistors in parallel to do that. We can only use one resistor, and that's more than enough. We don't need to use two resistors, just one will do. So basically, in this circuit, having a load resistor is completely redundant. And there's another circuit that we can discuss, namely this one. We have our usual voltage source, VI, connected in series to a resistor, and a diode. This diode resistor connection is in parallel, but also in parallel to the diode we have our good friend, the load resistor. So what happens here? Well, the output is still measured like in the previous circuit, but this time across the diode itself. And in this circuit, our load resistor will influence the circuit. We know from the last course that our diode has two states, on and off state. In the on state, if you remember from the last course, it said that the diode in the on state behaves much like a regular wire. So let me remind you about that. Anode and cathode, okay. It behaves much like a regular wire in the on state. Meaning, if this diode were to be on, our circuit would be short-circuited. So we wouldn't have a diode here, we would have a just a simple wire. And because of that, our output, no matter the input, would always be 0. If we were to have a regular wire here instead of a diode. Meaning that basically the diode is rendered useless. We cannot use a diode here. In the off state, however, the diode becomes an open circuit. Meaning there is no current or voltage going through this wire anymore. So then we can only work with this circuit when the diode is off, because if we work with this circuit when the diode is on, we're basically short-circuiting the input, meaning the output will always be 0, so there's no use for that. So we can only work with the diode in the off state. But what's the use of working with the diode in an off state? Well, there isn't. And that's because in the off state, our circuit basically becomes nothing more than a voltage divider. So as you can see, the diode is completely useless in this case. It has literally no use. So for our voltage divider, what's going to be the output? What's going to be the output for our voltage divider? Well, it's going to be, according to the voltage divider formula, VO will be RL over R plus RL multiplied with the input voltage. So this is the new value for the output voltage, or the value for the output voltage of resistor or voltage divider. If we look in our circuits, we have this circuit already made here. So like I said, in this situation, when it comes to the second circuit, we can absolutely ignore the diode, because if the diode were to be on, and we're only interested in working with the diodes in the on state, this circuit would always have a 0 voltage output, because it would be short-circuited. The input voltage would be short-circuited. So then we can only work with a resistive divider in this situation. And because of that, let's see what happens when with the input and the output across our voltage divider circuit. It's something like this. With green we have the input, and with red we have the output. And what you'll notice is that the output only goes up to a certain value. It doesn't go up to 10 volts, it goes up to 5 volts. This is because if we were to compute the output voltage for each resistor having 1 kilo, we'd get that V out, or VO, is 1 over 2 times 10, which is equal to exactly 5 volts. 10 is the input voltage, RL is 1 kilo, and 1 plus 1 kilo is 2 kilo. So we have exactly 5 volts. So then our output is limited to 5 volts, as we can see in this waveform here. But we can also work with the diode, and we'll see that this thing where the voltage is limited to 5 volts will still remain, but the thing that will change is the shape of the output voltage. Again, this is the green one is the input. Change that. And the red is the output. So you can see it still has a 5 volt amplitude, but the voltage drops below 0, and we're basically never ever working with negative voltages. So if you were only to focus on the positive half of this wave, you'll see that we can actually use these two resistors to limit the amplitude of the output voltage. But again, if the diode were to be on, theoretically it is considered as a simple wire. So it's as if this diode never existed, and regardless of the input, the output will always be 0 volts, as shown in this graph. So that's why using a load resistor is considered a drawback. So far we've discussed of what happens in terms of voltages. We can also go further and discuss what happens in these circuits in terms of currents. So actually, before I go ahead and do that, you should remember that the output voltage is only a fraction of the input voltage, and this changes the same time RL does. We're talking here about the second circuit. Therefore, the second circuit is dependent on the load resistor, which can be a drawback, like I said. And in order to reduce this disadvantage, the ratio RL over R plus RL, this one, should be approximately equal to 1. So you want this to be as close to the value of 1 as possible. And that means that RL, the load resistor, should be much greater than the value of the regular resistor. Going forward and talking about currents, for the first circuit, this one, the current is consumed only when the diode is on. Of course, when the diode is off, there's no current consumption. So for when the diode is on, the current through the diode, according to Ohm's law, is VI, the input voltage, over R in parallel with RL. If you want to go even further, it is VI over R equivalent. We know this from Ohm's law. For the second circuit, when the diode is on, the current, I'm going to write it right up here, the current through the circuit, ID, is equal to VI over R. When the diode is on. And when the diode is off, the current is equal to VI over R plus RL. So these are two more notions that you should remember. Actually, let me see. Okay, that's good. The fact that there is current consumption even when there is no voltage across the load can also be considered a drawback. So make sure to remember that as well. Going forward, we're going to discuss a little bit about prohibited connections between diodes, voltage sources, and resistors. Theoretically speaking, how we should be careful in how we connect our diodes in the DR switching circuits. Why? Well, let's take this first circuit. For example, We have a voltage source. We have a diode in parallel this time to our voltage source. And in parallel we have a resistor. So what happens here? Well, when the diode is in the on state, our diode and our resistor are in parallel. And that means that the input voltage should be greater or equal to 0, and the voltage source is short-circuited by the diode in its conduction state as the current through the diode tends to infinity. Or like I said before, a diode in the on state is considered to be a wire, meaning instead of this diode we would have a regular diode, and the input or the voltage and the voltage source is basically short-circuited. In the off state, there's basically no reason to talk about it because there wouldn't be a wire here, it would be a gap. So basically our circuit becomes a voltage source connected to a resistor, so we don't need to talk about that. The solution to this problem is to use instead a current source. So by using a current source, as I'm showing you now, things are changing. So if we're to use a current source instead, this circuit would work. And it's very, very simple. It's a very simple solution. Because this offers as input a current source and not voltage. But also you should remember to not connect current sources such that during normal operation the circuit might become an open circuit. In this case, everything is okay, so we don't have to. We can actually use this circuit. We cannot use this one, and I just explained why. But you should also be careful in how you connect current sources, so that they're not short-circuited. And by that I mean, imagine a current source connected in series to a diode. When this diode is in its on state and enters conduction, it basically becomes an open wire, and this becomes a short circuit, and thus we are short-circuiting a current source, which is not a good thing. Okay, so we cannot use this either. So be very, very careful how you implement your circuits to make sure that they work. Okay, with that we are pretty much done. Next time we'll discuss about so for next time I'll discuss about the constant voltage drop model of the diode. Constant voltage drop model of the diode. and what it means. So that's the subject of our next discussion. And soon we're also going to have a course dedicated to solving problems with diodes and diode circuits. That being said, I hope you enjoyed this course. I hope you understood everything that I presented you, and I will see you all next time.